morning, sir. Myself, Sagang Reddy from Mechanical Engineering, second year. Subject: Manufacturing Processes. Topic: Plastic deformation in metals and alloys, recoveries, recrystallization, and grain growth. Introduction to plastic deformation. Plastic deformation is a permanent change in shape that occurs when a material is subjected to stress. It typically occurs beyond the yield strength of the material, leading to dislocate movements. Understanding these properties is crucial for the mechanical properties of metals and alloys. Mechanism of plastic deformation. Dislocation slips is the primary mechanism of plastic deformation in recrystalline materials. Twinning is another mechanism that can occur partially in hexagonal closed packed metals. The balance between these mechanisms influences the overall ductility and strength of the material. Overview of recovery. Recovery is the first stage following plastic deformation, allowing for some stresses reliefs. It involves reagreement of dislocations and other defects with sufficient microstructure changes. This process can lead to a slight increases in ductility and reduce in internal stresses. Mechanism of recovery. Dislocation climate allows dislocations to move out from their slip planes, aiding in stress relax. Vacancies diffusion plays a key role in the recovery processes. Factory dislocation movements. The recovery processes generally occur at elevated temperatures but below its recrystallization temperature. Overview of recrystallization. Recrystallization is a process by which deformation grains are replaced by a new set of strain-free grains. The transformation occurs after recovery and is influenced by temperature and time. Recrystallization enhances the ductility of the material by creating a finer grain structure. Conditions for recrystallization. Temperature is a critical factor as recrystallization typically occurs at 0.3 to 0.5 times the melting temperature. The amount of prior plastic deformation also influences the recrystallization rate and grain size. Increased deformation generally leads to a finer grain structure upon recrystallization. Mechanism of recrystallization. New grains can nucleate at the boundary of deformed grains or within the grain themselves. Grain growth during the recrystallization can occur as grains consume a smaller one, leading to a stable microstructure. The process is typically activated, meaning that higher temperature can accelerate recrystallizations. Factors affecting recrystallization. Impurities and alloying elements can significantly alternate recrystallization's behavior and kinematics. The degree of deformation and the initial grain size are also crucial parameters. The presence of second phase parcels can hinder growth and affect recrystallization. Overview of grain growth. Grain growth follows recrystallization and involves the increasing in average grain size over time. The process occurs at elevated temperature and can affect mechanical properties. Understanding grain growth in the for optimizing the properties at metals and alloys. Mechanism of grain growth. Grain boundaries migrate the primary mechanism driving grain growth. Larger grains grow at the expense of smaller grains, reducing the total grain boundary area. The rate of grain growth is influenced by temperature, time, and the presence of other phases. Factors influencing grain growth. Temperature is a significance factor. Higher temperature generally leads to increased grain growth rates. The initial grain size also plays a role where finer grains leading to slower growth. Allowing elements can either promote or grain growth depending on their solubility and distributions. Effects of grain size on properties. Small grain sizes typically enhance strength due to half-finance relations. Ductility can also be influenced by grain size, with too small and grain size potential leading to brittleness. The balancing of grain size recoveries and recrystallizations is the key optimizing mechanical properties. Applications of recoveries, recrystallizations, and grain growth. These properties are crucial in manufacturing processes such as rolling, forming, and annealing. Understanding these phenomena allows for improving material design and performance in applications. Tailoring grain structure can enhance properties in automotive, aerospace, and construction materials. Experimental techniques for studying microstructure. Techniques like electrons microscopy and X-ray diffraction are used to analyze microstructure changes. These methods providing insights into the grain size, shape, and distributions after deformation and thermal treatments. Understanding these techniques is essential for material science research and developments. Case study: Aluminum alloy. Aluminum alloy are widely used due to their excellent strength to weight ratio and corrosion resistance. The recovery and recrystallization process are crucial for achieving desired mechanical properties. Understanding grain growth in these alloys can lead to improved performance in various applications. Case study on steel alloy. Steel alloy exhibits significant changes in properties due to recovery, recrystallization, and grain growth. The presence of carbon and other alloying elements can significantly impact these properties. Optimizing heat treatment processes can enhance the performance of steel in structural applications. Challenges in industrial applications. Controlling grain size during processing can be challenging due to the complexity of alloy system. Variations in the process conditions can lead to inconsistency of in mechanical properties. Developing dedicated models for this phenomena is an ongoing areas on research. Future trends in metal processing. Advances in computer material science are allowing for better precision and controlling the microstructure elevations. New processing techniques like additive manufacturing introduce novel changes and opportunities for grain structure control. Research into nanostructural materials is opening new avenues for enhancing mechanical properties. Summary of key concepts: plastic deformation, recovery, recrystallization, and grain growth are interconnected processes affecting materials. Understanding these processes is essential for optimizing the performance of metals and alloys. Continuous research and innovations are virtual for additive metal processing technologies. Conclusion and questions. The study of plastic deformation and associated phenomena is crucial in material science. Future advancements with continues to refine our understanding and applications in various industries. Questions and discussion are encouraged to future exploration these important topics. Thank you.